So I want to talk a little bit about writing a Lewis structure and kind of trying to figure out when to use a single, double, and triple bonds, and then some kind of other overall tips. Now, if you move on in chemistry, you'll learn even more tips and learn that this process is a little bit more complex. You might get to explore molecules that violate the octet rule. But for simplicity, we're gonna go with kind of the most straightforward of examples. So let's say we were trying to write the Lewis structure for, let's say, ethane. So there's the chemical formula for ethane. So one of the first things that I would kind of consider is just your overall, what are your Lewis structures? What are you, of just the atom itself? You know, there's carbon, but we know we have 2 of them. So that's really 8 valence electrons between the 2 of them. I'm just showing 4, so maybe I'll put a, times 2. And then we have hydrogen, which only has 1 valence electron, but again, we have that times 6. So I've got 6 valence electrons through my hydrogens to work with and 8 through my carbons. So the big thing to remember is that I want to fill everyone's valence shell. Now for carbon, that's going to mean 8 valence electrons. That's not how many it has right now. That's how many it is when it is the most stable, when it has the same electron configuration as its nearest noble gas. So that's kind of why we call it the octet rule. For hydrogen, it's only 2. So hydrogen, think about hydrogens, the Bohr model for hydrogen. So there we've got, our H, and then we have 1 valence electron in that first shell. But that first shell actually only holds 2. And so if we get another one right here, then we actually have filled the valence shell of it. So it's 2 for hydrogen and 8 for carbon. So let's say I start by, let's just assume that my 2 carbons are going to bond. And if you want to, sometimes I like to, we usually just show it with a line, but sometimes I like to go ahead and put a dot there to remind me this carbon gave an electron and this carbon gave an electron, and they're sharing it. And so you can see how that developed. Each of these carbons still would have its other 3. And you can tell here I haven't in any way filled its valence shell. Even if this carbon gets to share and count this one, it still only has 5. But I can start to see, based on like that Lewis structure, where these 6 hydrogens might end up. Because notice I have exactly 6 sides of the carbon kind of open for sharing. So let's, rather than dots, let's draw a single bond to a hydrogen in each of those locations. So each of my carbons has shared one of its valence electrons with another element, and that element is sharing an electron back. So now these lines then are 2 electrons. So let's see if each carbon has a full valence shell. So here's our carbon, 2, 4, 6, 8. So that carbon has a full valence shell. And then this carbon, 2, 4, 6, 8. You have to remember that this line represents 2 electrons. 1 kind of brought by the hydrogen and 1 brought by the carbon. So my hydrogens each only have 2, 2, 2, 2, 2, 2, 2. But as I said before, that's all hydrogen wants. So in this molecule, all the atoms can have a full valence shell through single bonds only. So that means they're sharing, they each contributed 1, and that they're sharing then the 2 pairs. So 1 electron from this atom, and then we share, and that's what a single bond means. Now, what if I try to draw the Lewis structure for a chemically related compound, also made of carbon, but it happens to have fewer hydrogens? So you might kind of notice we're going to have a problem if I bond my 2 carbons together, and I bond, let's say, put a hydrogen on each of them, kind of like I was before. So there's the chemical formula of this. But I technically, each of my carbons still has an electron that isn't being shared, and they do not have a full valence shell. This is 2, 4, 6, 7. So this carbon is actually, it's closer to having a full valence shell from before, but it isn't. So what if the carbons got a little bit closer together and moved this electron each of them down here, and so that they were between them sharing not 1, 2 electrons, but 1, 2, 3, 4. So let's draw what that Lewis structure would look like. So I haven't used more valence electrons than anybody actually has. So now let's count 2, 4, 6, 8. 2, 4, 6, 8. Each carbon has a full valence shell. I'm using the same chemical formula, and each of my hydrogens has a full octet too. So this is called a double bond, and I might have to use a double bond in order to fill someone's octet. Let's look at another situation. A common one, we could continue on with hydrogen if we want. Oh, we'll go ahead and do that. Carbon 2 again. Let's get rid of another 2 hydrogens. So this molecule here is commonly known as acetylene, so like in acetylene torches. So let's kind of go through just like we have been. Let's single bond the 2 carbons. Let's attach hydrogen to each of them. So that would leave this, because we started here, but we're sharing. So one thing, carbon does not tend to have lone pairs. In fact, we're going to add that down here. Elements that commonly have lone pairs around them, not carbon. So carbon tends to have 4 bonds in some manner, whether that's single bonds, double bonds, or triple. So you can imagine, well, what if we just shared again? You move your electron down here, you move your electron down here, we'll share. Well, that still doesn't fill the valence shell, and we still have carbon with some lone pairs. So let's get even closer, because they do have to get a little bit closer every time in order to have those shells overlap. So we could actually share a total of 6 electrons, and that looks like this. So 2, 4, 6, 8. Carbon has a full shell, and this carbon has a full shell. And I'm drawing it this way to reflect the linear geometric shape according to the Vesper theory. So this is then a triple bond. So let's talk about elements that commonly do multiple bonds, because hydrogen doesn't do that. And that's because that would be 4 electrons. Remember, hydrogen only wants 2. So let's talk about the elements that you're likely to see forming these double and triple bonds. So carbon is one of them. So carbon, you might see it with 2 double bonds. It could also be 1 double bond and 2 single bonds. That's like we see here. And another, you could see carbon with a triple bond to something else and then a single bond on the other side, like we see here. So these are possibilities when you're developing your Lewis structures that you could consider for carbon. Some other options, or some other elements that you're likely to see multiple bonds on, is oxygen. Oxygen can do double bonds. So you could see oxygen double bonded to something else. A nitrogen will do a double bond and a single bond. Nitrogen also can do triple bonds too. And there are a few others, especially those in the same group. So like sulfur is in the same group as oxygen, so sulfur also can do double bonds. Phosphorus is in the same group as nitrogen, so you might see these patterns for phosphorus as well. And that kind of goes back to the periodicity we see in the periodic table. Elements in the same group have similar chemical properties, and same number of valence electrons. So that means that their bonding pattern is sometimes very similar. So there are some elements that we don't commonly see, like hydrogens and the halogens, and then others that are a little bit more likely. And that can also help you with your Lewis structures. If you're struggling to fill everybody's valence shell, consider what elements you have and try some alternative structures. I want to talk about elements that commonly have lone pairs around them. And I said not carbon, so that's a non-example. And I kind of already started to do that over here. Oxygen tends to have 2 lone pairs, and we see that like in water or in oxygen gas. So oxygen gas, the Lewis structure of that is 2 oxygen atoms double bonded, and then they have their lone pairs. So oxygen, and therefore sulfur, anyone in the same group we'd expect to have kind of potentially similar. Nitrogen is also very comfortable with a lone pair, and so you see that in a lot of its structures, like in ammonia, where it's single bonded to the 3 hydrogens, or even nitrogen gas, which is 2 nitrogen atoms triple bonded together, but each having a lone pair. And the lone pairs matter too in developing our Lewis structures, but also determining the molecular geometry. So I hope this clears up a little bit that objective on single, double, and triple bonds and drawing Lewis structures.